All right, so the topic for today is the root locus. The idea behind the root locus is basically you've got some controller and a plant in a feedback structure, like we've been talking about all semester, like so. And the idea, of course, is when you compute the closed loop transfer function, that is the transfer function from R to Y, which is your overall closed loop transfer function, the poles of that transfer function are computed by the characteristic equation. So that 1 plus Cp equals 0, you solve for S, those are going to give you the closed loop poles. The main concept is that the controller itself partially defines those pole locations. So it stands to reason that if you adjust the controller, the closed loop poles are going to change. And as we know at this point, the closed loop poles essentially dictate the behavior of the system. So we'll start with a very simple example here. Plant is first order. Controller is a simple gain, just like just like we always do. And if we were to then compute just by plugging into Cp over 1 plus Cp, get our closed loop transfer function, we get the following closed loop system right here. And so this is our characteristic function, s plus the quantity k plus 1. Set that equal to 0 and solve for s. And what we have is basically we can make ourselves a little table that tabulates the closed loop pole as a function of the gain that you plug in. Right? So a gain is just a real value that you get to adjust as a control designer. Now, if we imagine, if k equals 1, you set up the equation s plus 2 equals 0, then you've got a pole at s equals negative 2, which on the s plane is going to be right about here at negative 2. So you've got a pole right on the real axis for a value of k equals 1. Imagine filling in this table, right? So if k is equal to 2, now the closed loop pole changes to s equals negative 3. The pole is moved, and it's moved in this particular direction, sort of horizontally to the left. Obviously, we can keep filling in this table, but you'll start to see the pattern here, right? Obviously, you could do integer values or decimal values. And basically, for all values of k, you could start to fill in every pole location. And if you take this to the extreme case where you do it for a continuum of k values, i.e. every possible value greater than 0, what you'll essentially find is a continuum of pole locations in the S-plane. Eventually, those pole locations will trace out. Let's be fancy here. Eventually, those pole locations will trace out sort of like a line, right? And the direction of that line is very important because the direction of that line indicates the direction of the closed loop poles as you increase the k parameter. So that's the main idea behind the root locus, is that as you adjust the as you adjust the control gain, the closed loop poles are going to move, and the root locus tells you precisely how those poles are going to move around in the S-plane. Okay? This was a very simple example of a first order transfer function where if you made this table, it's very clear how that pole will move around in the S-plane. But it's not always quite so simple. If you have more complex transfer function, third order, fifth order, eighth order, and so forth, it can get a little bit tricky to make a corresponding table like this to quickly visualize how the poles are going to move around in the S-plane. By the end of the lecture today, I'm going to give you a set of rules that allows you to basically sketch the root locus without having to make a table like the one here. And those set of rules apply to basically any plant controller combination that you could come up with. So the set of rules to sketch the root locus is very powerful. But the power doesn't become very apparent until you understand sort of the benefit of the root locus. I mean, if you were to take an example like if we were to say have a root locus plot that looked a little bit different, for example. Root locus plots can come in many different varieties. In fact, they start to look awfully strange at some point. Here's one example of what you may see for a root locus. You might have 3 poles like so, and the root locus branches may do something like this. I'm just picking arbitrary colors here. They may do something like this. So one branch may go this way, and then the other 2 may go this way and this way. And of course, this is, again, the location of the 3 closed loop poles in this problem as a function of increasing that particular gain k. Now, this one, this particular root locus is alarming because you'll notice that 2 of the branches actually enter into the right half plane. So by looking at this root locus alone, you can verify that, for some critical value of k, the closed loop poles will actually move, or 2 out of the 3 closed loop poles will actually move from the left half plane into the right half plane, thereby destabilizing your system. So this is just one example of sort of the use and the utility of the root locus plot as a control design and analysis tool. Okay, so to summarize so far, the root locus is a plot that basically indicates the closed loop pole location as a function of increasing one gain parameter in your controller. All right, so the next idea before we jump into that set of rules that allows us to sketch the root locus is in order to use this particular set of rules, we actually have to have the characteristic in a very particular form. And that particular form looks like this. Okay, so if you imagine, the closed loop denominator is generally 1 plus Cp for the transfer function Cp over 1 plus Cp. And in that case, what you would do is you would plug in whatever controller and plant transfer function you have and basically ask yourself if it's in this specific form. In other words, it's 1 plus k, right, the gain by itself, times a bunch of other stuff, right? And this bunch of other stuff is basically, it's not necessarily equal to Cp. It will depend on the specific controller and plant that you plug in to your characteristic function. And the thing is, the root locus rules, I'm going to call it RL, the root locus rules apply to this particular transfer function, whatever that happens to be. It's neither the plant nor the controller nor the product of the two. You just have to plug in and see what you get. Okay, so in the previous example, we had C was equal to K, P is equal to 1 over S plus 1. So you simply plug in to 1 plus Cp equals 0, and then ask yourself, is it in the right form? In other words, 1 plus K times a bunch of other stuff. In this case, it's 1 plus our controller, which is K, times our plant, which is 1 over S plus 1. And so looking at this equation, it is indeed in the form of 1 plus K times a bunch of other stuff. And that bunch of other stuff is what you call L of S. Okay, it's not equal to the open loop transfer function as it has been in the past. Okay, so this is sort of a special root locus transfer function. And this L of S is the transfer function that we are going to apply the closed loop. We are going to apply the root locus rules for. Let's look at another example of this, because it's not always as simple just to plug in and be done. So here's an example where the controller, let's start with the plant. The plant is basic, it's first order, but the controller, for whatever reason, we decide to use a pole at negative k. Right? Remember, the controller is just a transfer function that you can specify based on your control design criteria. So this is the chosen control and plant for this particular example. Now when we plug into 1 plus Cp equals 0 here, we get 1 plus C, which is 1 over S plus K, times P, which is 1 over S plus 3. So this is definitely not in the form of 1 plus K by itself times a bunch of other stuff. Okay? In this case, you have to manipulate this equation first to produce an equation that looks like 1 plus K times L of S. And then once you have that L of S, then you can go ahead and apply the root locus rules. Okay? So the way to do it in this case would be, you do a little bit of algebraic manipulation here. You can multiply both sides of this equation by S plus K, which gives you S plus K plus, and then they'll cancel here, so you're just left with 1 over S plus 3. And then on the right hand side is still 0 because it's multiplying by 0. What you'll then do is you can kind of group. Okay, so what I'll do is I'll isolate the K. So I'm going to rearrange this S plus K, and I'll call it K plus S. Right, so I didn't change anything, but I'm going to group this stuff together. And then I'm going to divide both sides by that whole parenthetical. So if I call this asterisk, I'll divide both sides of the equation by that. And what that gets me is the 1, right? So this parenthetical divided by itself gives me 1. On the right-hand side, I still have 0. And then over here, I've got k divided by this parenthetical. So it becomes k over s plus 1 over s plus 3 plus 1, which is getting a little bit messy, but what you can see is that we're starting to construct this form of 1, which is here, plus k. So I've got my k here in the numerator, which can easily be factored out. And then the L of S is this mess of 1 divided by the quantity s plus the fraction 1 over s plus 3. So we can finally clean this up just a little bit. So 1 plus, if I factor out this k, I'm left with 1 over this entire parenthetical down here, which I can simplify to s plus 3 over s squared plus 3s plus 1. And now we have it in the proper form of 1 plus k by itself times a bunch of other stuff. Okay, and the important thing here is that this bunch of other stuff right here in that parenthetical, that becomes the L of S that we're going to apply the rules of the root locus for, right? So it will allow us to, this L of S and the rules that I'm about to show you will allow us to sketch that plot of the S-plane with those branches going around in different directions, which ultimately becomes a very useful analysis tool. Okay, so the rules for drawing the root locus. There are, well, there's 6, but they start at number 0, which is strange. Rule 0 is actually a very trivial one. Okay, Rule 0 for drawing the root locus is basically that the root locus branches and the root locus plot symmetrical about the real axis. Okay, that's the first rule. It's rule 0 because it's almost just a fact. It's a sanity check to make sure you're drawing your root locus properly. If you think about why this is the case, I drew one example that looked kind of like this, but then I also came up with another example that had maybe 3 poles and 2 branches go off in this direction. Any root locus that you draw must be symmetric about the real axis, and the reason is the root locus itself is nothing but a collection of closed loop pole locations as a function of increasing the gain parameter k. Now, poles on the real axis, those are what they are, but poles in the complex plane are complex poles, which means they always exist in conjugate pairs, right? So if there's a pole here at, say, minus sigma plus omega j, there must also be a pole down here at minus sigma minus j omega, right? So the reason this is true is that poles always exist in conjugate pairs, which makes sense, right? So poles are always complex conjugates if they have an imaginary component, and if they're on the real axis, they're just on the real axis. So for that reason, you're always going to have a root locus plot that is symmetric about the real axis. So that's rule 0. Rule 1 is, okay, so rule 1 tells you basically the destinations of all of the root locus branches. Okay, so the setup here is L of S has M zeros and N poles. And N is always greater than or equal to M, because if that weren't the case, you'd have a transfer function that is non-causal, which can't exist in real life. So N, the number of poles, always has to be greater than or equal to the number of zeros. And then the idea of rule 1 is the following. The root locus always starts, right? The branches always begin from the N poles. Right, so the branches always start at the poles of L, and then M of them, right? So however many zeros there are in the transfer function L, that many of the root locus branches will approach those zeros of L of S. And then because N is always greater than or equal to M, there may be some leftover branches. So N minus M branches those approach infinity. Oh my gosh. Those approach infinity. Right, so right, one of the examples that I keep coming back to is in this case here. You have 3 poles, right? In this case, N equals 3, M equals 0. There are no zeros for this particular L. Otherwise, you would have seen an O on the S-plane. In this case, N is 3, M is 0, so 3 branches approach infinity. And M branches, the number of zeros, in this case is 0. So 0 branches approach the non-existent zeros. So in this case, it makes sense that all 3 of these branches approach infinity. Right? So that's one example of the root locus. That's one example of how rule 1 applies to the root locus. We also did the very first example where we made that little table, and we actually computed a whole bunch of pole locations on this little table, right? So we said, wow. We said when k is 2, there's a pole at -3. When k is 3, there's a pole at -4, and so on. Well, that traced out this branch that basically went straight to the left, right? So in this case, that transfer function had 1 pole, and again, 0 zeros. There weren't any zeros. Okay, so 0 of the branches should approach the 0 zeros because there aren't any. And then 1 minus 0 of the branches should approach infinity. So in this case, that one branch just approaches infinity off to the left. Okay. So what we can do at this point is basically Okay, so there's 6 rules I said, 0 through 5. I've outlined 0 and 1 so far. So let's make sure we understand these two before we move on. Okay, so between between rule 0 and rule 1, we can look at a couple of examples and sort of understand or analyze what's going on with all of these. Okay, so I've got an example where let me just write it out first. So in this example, L of s is equal to s plus 1 over s squared plus 9. This transfer function has zeros. There's 1 at -1, right? Set the numerator equal to 0 and solve for s. But there's 2 poles, right? P1 and P2. If you set the denominator to 0 and solve for s, you get plus and minus 3j. Right, so there is m equals 1, 0, and n equals 2 poles for this example. Now let's try and see what the root locus for this particular L of s might look like. Here's one example. The first thing you always want to do when sketching your root locus, by the way, is to plot all of the poles and zeros of L of s. It'll help sort of visualize the branches, and it'll give you a starting point. Okay, so I've got pole here and here on the imaginary axis, and then there's a pole at, there's a 0 at -1. So this is what my S-plane looks like. Let me sketch this out a couple of times here. We'll look at 3 different scenarios. So x, like so. So 3 different scenarios. What I'll do is try and sketch out the root locus branches in a variety of different ways so you can see which ones satisfy which rules and which ones do not. Okay, so in this first example, remember that rule 0 says the root locus has to be symmetric about the real axis. So here's an example where the branches come down, right? The branches always leave from the poles and head outward from there. Okay, so this is one scenario. Is this a proper and valid root locus, would be the question. And the answer would be no. It does satisfy rule 0, right? Because the branches are symmetric. The root locus is symmetric about the real axis. But according to rule 1, m of the branches, right? So in this case, one of the branches should approach the 1, 0 of the transfer function L. And then n minus m, in this case 2 minus 1, one branch should approach infinity. Okay, so in this case, rule 1 is violated. Rule 1 is violated, and so it's not a valid root locus, right? A valid root locus has to satisfy all rules 0 through 5 concurrently. Okay, so let's take a look at a second scenario. In this case, we've got this scenario where one branch, so m is equal to 1, so one branch should approach the 1, 0. And then the second branch, n minus m, so one of the branches should approach infinity, like this, like so. Okay, so this satisfies rule 1. The question again is it a valid root locus? The answer again is no, because in this case, even though it satisfies rule 1, it does not satisfy rule 0 because it is not symmetric about the real axis. So this also fails because it does not satisfy rule 0. So the question becomes, how on earth do we sketch these branches so that it satisfies both rule 0 and rule 1? And the answer is the following. The only way rule 0 and rule 1 can both be satisfied concurrently is for one branch to come out of the pole. Actually, both branches will come out of both poles simultaneously because it needs to be symmetric about the real axis. So they'll head out this way, And they'll actually have to meet somewhere on the real axis at a common point, right? Because it's got to be symmetric. And then at that point, one branch will head off and terminate at the 0, thus satisfying rule 1. And the other branch will head off to the opposite direction to infinity, also according to rule 1. Okay, so what I might do is draw these sort of two different paths, so two different colors. And it doesn't actually matter. The question always is, well, which branch goes to the left and which goes to the right? It doesn't matter because they represent the full set of poles for the transfer function L. Okay, so if one branch goes to the left, that implies that another goes to the right, and as long as both branches are there in existence, then it doesn't matter which one is which. Okay, so this guy right here, this root locus picture, is both symmetric about the real axis and also satisfies the rules or the implications of rule 1. So this one here is a valid root locus. Okay, so let's look at rule 2 now. And to illustrate rule 2, I can start with the question that we just looked at. Okay, so in the previous example, we found that there's really only one way to draw the root locus so that it satisfies both rule 0 and rule 1. Actually, let me do it this way. I've got the colors, I may as well use them. Okay, so one branch has to come down, and maybe this is the one that goes off to infinity, and then another branch comes up, symmetric to the first one, but this time terminates at the 0. Okay. By the way, the direction of the branches is critical when drawing the root locus plots. You need to make sure you indicate what is the direction of these branches because that corresponds to the direction of increasing the gain, right? So as the gain value is increased, the poles move along these branches in the direction indicated on the root locus. Okay. Okay, so this was the one possibility that satisfies rule 0 and rule 1. However, I'll present to you another option that looks like this. So we still have our poles here and our 0 here, but I would argue that the following root locus plot also satisfies rule 0 and rule 1. Okay, the only difference here is that the point at which the branches break into the real axis occurs to the right of the 0 at -1 instead of the left. And either one of these both satisfy rule 0 and rule 1. Okay, so the question is, which one is the valid root locus? Some of you may be thinking, well, this one can't be. There's something fishy about this one. And the comment that usually comes up is that, well, one of these branches goes into the right half plane, which implies instability. And my answer to that comment is, well, so what? Right? For some values of k, some systems do in fact go unstable. So the fact that a branch of the root locus exists in the right half plane is just a fact of life. It doesn't mean that it's somehow invalid. It just means that you need to be careful because for some critical values of k, you will actually destabilize the system. Okay, so these are both valid according to rule 0 and rule 1. However, there can only be one truly correct root locus. And the only way to answer that is to look at rule 2. Okay? Rule 2 is a little bit interesting here. So rule 2, let me just write it out here. Okay, so it's a little bit wordy, but it says that the portion of the real axis to the left of an odd number of poles and zeros is part of the root locus. Okay, so it's kind of it's a little bit tricky. You have to sort of stare at this for a while and understand how how it works. And I think the easiest way to apply Rule 2 is to do sort of this vertical line test. Okay, so what I mean by that is if we look at our example here, we basically have our poles and zeros of L of S. Okay, so we plot those out. And what you do for this vertical line test is you essentially you go all the way to the right. That's not going to be bright enough. You go all the way to the right past the furthest pole and zero. So you start way, way out here. Okay, and you sort of pretend that you're standing right on that line looking down onto this plane of poles and zeros. And then you ask yourself the question, or you make the statement that right now I am, at this point right here, I am to the left of 0 poles and zeros, right? So in other words, there's nothing over here, right? There aren't any poles and zeros over here. So I am presently to the left of 0 poles and zeros, right? There's nothing to the right of me, in other words. And because 0 is not an odd number, that implies that that point of the real axis right there is also not considered to be part of the root locus. It's a little bit strange. Okay, so let's see how this applies. A vertical line test itself means that you would basically sweep this vertical line to the left and pass through all of the poles and zeros, asking yourself the same question the whole time. Okay, so really nothing else interesting happens until we cross the imaginary axis, in which case we would be standing on this vertical line. And in this vertical line test, you would say to yourself, well, right now I am to the left of 1, 2 poles and zeros, right? I am to the left of 2 poles and zeros at this point right here. 2 is also not an odd number. Therefore, this point right here is also not considered to be part of the root locus. Now, if we were to move this line a little bit more to the left, such that we're now over here, the story would change a little bit. Because now I am to the left of 1, 2, 3 poles and zeros. Right? I'm standing here. I am to the left of 3 poles and zeros. 3 is an odd number, and therefore this point on the real axis is considered part of the root locus plot. And so the same logic applies if I move incrementally over, and essentially anywhere to the left of this 0, all this part of the real axis forever in this direction should be part of the root locus. That's what Rule 2 tells you, right? Rule 2 tells you what part of the real axis is considered to be part of the root locus plot. Okay, so Rule 2 tells us that basically all this shaded region here in red on the real axis, that should be part of the eventual complete root locus plot. So now if we look back at our 2 options up here, we had 2 options that satisfied both Rule 0 and Rule 1. And like I said, there can only be one truly valid root locus. So with Rule 2 in mind, the only valid root locus is the one that we drew here on the left. This guy can't be true because this root locus over here had a portion of the root locus that disagreed with Rule 2. Rule 2 said only the part of the real axis to the left of this 0 should ever be considered part of the root locus, which agrees with this plot on the left. So this is how Rule 2 applies. Okay, so in Rule 3, let's look at one scenario here. So all we're going to do is include one additional pole, and in this case we find that m equals 1 and n equals 3. There's 1 0 and 3 poles. So very quickly, just to illustrate the idea here, we've got two imaginary poles at plus or minus 3j. There's one real pole at -2 and 1 0 at -1. Okay, so according to our rules 0, 1, and 2, the root locus plot may look something like this. For example. Okay, so let's ask ourselves, does this satisfy all three rules so far, 0, 1, and 2? Well, what I've sketched here is symmetric about the real axis, so it satisfies rule 0. According to rule 1, one of the branches should approach the 1, 0. So this is a branch that leaves from a pole and terminates at a 0. The other two, so n minus m, which is 2, should approach infinity. So two of the three branches should approach infinity. So that satisfies rule 1. Is rule 2 satisfied? In other words, the part of the real axis that agrees according to rule 2, is that also valid? Okay, so if we were to do the vertical line test at a couple of different locations, let's do one way out here. Okay, so right here, way out to the right, I am to the left of 0 poles and zeros. So that portion of the real axis should not be on the root locus. That's good. In here, between the poles on the imaginary axis and the 0 at -1, I am to the left of, well, this should be an x. I am to the left of 2 poles and zeros. So this point here on the real axis should also not be part of the root locus. If we move to between the pole at -2 and the 0 at -1, at this point, I am to the left of 1, 2, 3 poles and zeros. Okay, so everything between this 0 and this pole should be part of the root locus on the real axis, right? And that's what we're seeing here, is that red branch right on the real axis that goes from the pole to the 0. Anything further to the left of the pole at -2, now I am to the left of 4 poles and zeros. 4 is not an odd number, and therefore none of this part of the real axis to the left of this pole should be part of the root locus. Okay, so I would argue that this picture of the root locus satisfies rules 0, 1, and 2 so far. Okay, the question remains. Okay, so the question is, we go back to rule 1, which says that n minus m, or 2 branches, should approach infinity. Okay, so the question is, I've got these 2 branches here, right, that are sort of going off to infinity, but do they go off to infinity this way, or do they go this way, or maybe this way, or this way, right? Right. The question is, how do the branches that go to infinity go to infinity? In other words, which direction do those branches go, the ones that go to infinity? That question is answered by rule 3. Okay, so rule 3 says that, let me go back to my standard developing color scheme here. Rule 3 says that n minus m branches, right? So in other words, the branches that go to infinity, those approach some asymptotes. Okay, and the asymptotes are defined by alpha, which is basically the point on the real axis from which these asymptotes originate. And you find alpha by adding up all of the poles, subtracting from it the sum of all of the zeros, and dividing by n minus m. And then the asymptotes themselves are defined by these angles, theta. Okay, so the formula is like this. It's 2l minus 1 over n minus m all times pi. And this is valid for l equals 1, 2, 3, all the way up to n minus m. However many branches you need, this is how many thetas you need to compute. Okay, and then the picture for this looks like this. Okay, so alpha would be a point on the real axis, and then the angle that the asymptote sort of radiates out from is given by your thetas. And there may be several of these thetas. In fact, there will always be n minus m of those thetas that you have to compute. Okay, so let's actually return to this example here, and let's figure out exactly how the branches that go to infinity, in fact, go to infinity. Okay, so what I'll do here is I will actually write down my poles. Okay, so I've got z1 equals -1. There are 3 poles, so p1 equals -2. p2 and p3 are plus and minus 3j, respectively. Okay, so it's always a good idea to just label all of your poles, even by subscripting them, especially for rules 4 and 5, which will come later. Okay, so what we have is basically, we have our pole 0 map. Okay, so here's 3j and -3j. We have a pole at -2, a 0 at -1, and we already know that this branch is going to start at the pole at -2 and terminate at the 0 at -1. The question is, these two branches that sort of come out of the poles at plus and minus 3j, where do they go? Okay, and so we're going to use rule 3 to figure that out. Okay, so what we have to do is to compute alpha. To compute alpha, you add up all the poles. Okay, so I have them nice and neatly arranged here, p1 through p3. So I got to add those up. -2 plus 3j minus 3j. From that, I need to subtract the sum of all of the zeros. In this case, there's only 1, and then divide by divide by n minus m, which in this case is 3 poles minus 1 0. Okay, so if you do this correctly, alpha is always going to be a real value because the complex conjugate portion of the complex poles will always cancel. Okay, so 3j minus 3j go away, and what I'm left with is alpha is equal to minus 1 over 2, so minus 1/2. For this problem, n equals 3 and m equals 1, so n minus m is equal to 2. This is the number of thetas that you're going to need to compute because that's the number of branches that approach infinity. Okay, so I'll need theta 1. Theta 1 can be computed by plugging in 1 for this L parameter in the 2L minus 1. So it's 2 times 1 minus 1 over n minus m, which is 2, times pi, which gives me pi over 2. So that's the first asymptote. I also need another one because there are 2 branches that go to infinity. This time, L is equal to 2. So it's 2 times 2 minus 1 divided by n minus m times pi, which in this case gives me 4 minus 1, which is 3 pi over 2. Okay, so those are the 2 asymptotes I'm going to need. Those asymptotes, they start at alpha. So alpha is here. We computed alpha to be minus 1/2. Right? So alpha equals minus 1/2, which is somewhere between the imaginary axis and the 0 at -1. From that point, we've got one asymptote that goes up at an angle of pi over 2, measured from the positive real axis, and then another one that goes at an angle of 3 pi over 2, which is actually going downward at 270 degrees. Okay, so those are the 2 asymptotes, and now what we have is a clear picture of how these two branches approach infinity, right? They approach along those asymptotes, like so. Right, so this picture over here, this is a much more accurate and complete root locus plot. Four out of the 6 rules done. We just need to talk about rule 4 and rule 5, and then we can actually do some examples on sketching the root locus. Okay, so here's an example, just to sort of illustrate the idea behind rule 4. Let's suppose we have a system with 2 poles and 2 zeros like this. Okay, so this is the poles and zeros of our L of S, and this is how they plot on the S-plane. Okay, in this case, in order to satisfy rule 1 in particular, what we need is, for this example, n is equal to 2. There's 2 poles, and I'm sorry, there are also 2 zeros. So according to rule 1, m of the branches, or 2 of them, should depart from the poles and then terminate at the zeros. And also, n minus m, which is 0 in this case, is the number of branches that approach infinity. Okay, so essentially what's going to happen in this root locus is our branches are going to, symmetrically leave the poles, and then they're both going to terminate at the zeros, right? That's how this root locus is going to look, right? According to rule 2, no part of the real axis should be included in the root locus, because at no point are you to the left of an odd number of poles and zeros, right? Okay, so rule 4 asks the following question. I know that the general idea is that there's 2 branches and they're both going to terminate at the zeros. Okay, the question is, okay, well, do they look like this, or do they look like this? Or do they look like this? Or do they look like this? Right? The question is, okay, what I'm trying to get at is, how do the branches leave the poles, and how do the branches terminate at the zeros? Okay, so what I can do is to try and illustrate a new parameter here. And the new parameter, there's 2 of them. One is called the departure angle, and that's the angle measured from an imaginary sort of positive real axis. It's the angle from which the branch departs the pole. So it's called a departure angle. Departure angle, which we denote by phi. Right? That's the angle measured from a positive real. Then there's also something called the arrival angle, which is the angle also measured from a positive real that the branch terminates at the zero. Okay, so that is usually referred to as psi, the angle, and is called an arrival angle. Okay. All Rule 4 does is to allow you to mathematically compute departure and arrival angles for the given root locus at hand. Okay, so what you're finding so far, hopefully, is that the series of rules, 0 through 5, are sort of gradually giving more specificity to the root locus picture. They're fine-tuning it and making it more accurate as you apply the rules. Okay, right, so 0, 1, and 2, those are all broad rules. You can generally sketch out the root locus. Rule 3 and Rule 4, those are very specific, and they tell you precisely how the root locus is going to be shaped. All right, so let me write out Rule 4 here. Rule 4 is by far the most tedious. There's a lot of kind of math involved that can stump you, but fundamentally, Rule 4 is 2 equations. right? It'll tell you the departure angle from pole K. That's a K. And the equation here is phi sub K is equal to a couple of summations. First, you're going to sum through all of these zeros, and it's the following equation. It's the kth pole minus the ith zero. So this, however many zeros there are, that's how many elements will be in this summation. Minus another summation that sums through all the poles. So pk minus pi. This will have as many elements as there are poles in the equation. And then there's a factor of plus or minus 180 degrees on the end. It doesn't matter which way you choose. Plus 180 is the same angle as minus 180. You're just going in the opposite direction. The arrival angle at 0 sub k, z sub k, is similar. The equation is similar, but fundamentally different. Okay, so it's also two summations being subtracted, plus or minus 180, but the first summation in this case is the summation through all of the poles. So from I equals 1 to n, it's the kth 0 minus the ith pole, minus this summation that sums through all of the zeros, plus or minus 180. Okay, so this is rule 4, just written down in plain mathematics. The following examples will show you how to use rule 4, which is really where the tricky part kind of comes in. Okay, so let's look at one example here. Let's do this one. So let's do one example here that will illustrate how to use rule 4. For the transfer function 1 over s squared plus 1 times s minus 1, we find that there are 3 poles and no zeros. More specifically, P1 is equal to 1, P2 is equal to j, P3 equals minus j. Okay, it's very important to write down and label your poles and zeros, especially when you're trying to apply Rule 4 and Rule 5. Okay, let's see. How many of the branches are going to approach infinity? Well, all 3 of the branches should approach infinity because there are no zeros for any of the branches to terminate. Okay, so what we need is to compute our alpha, right, which we can get by applying Rule 3. Alpha equals 1/3. And then we need 3 values for theta to get our asymptotes, which we can also get from Rule 3. Okay, and so far what the root locus looks like is this. Pole at positive 1, so this is unstable. And then 2 imaginary poles at plus and minus j. The root locus so far looks like this. We know that one branch is going to go to infinity along the real axis like so, because this is in accordance with Rule 2, which says that basically all this part of the real axis needs to be part of the root locus, because at any point to the left of this pole at positive 1, I am always to the left of an odd number of poles and zeros, whether it's 1 or 3. Okay. Question is, okay, I've got an alpha at 1/3. My asymptotes turn out to be 60, 180, and negative 60. Right? So when I compute all my angles, so I know that at 1/3, I'm going to get an asymptote that goes straight along the negative real axis, and then also two symmetric asymptotes at plus or minus 60 degrees. Okay? The only question that remains is how did these branches approach those asymptotes? Is it like this, or like this, or even more an extreme case like this, or like this, right? So that's the question. And in order to answer that question, I need to compute the departure angle at this particular pole. Okay, so it's very important to keep your labels of your poles in agreement with how you plot them on the S-plane. So I called the pole at positive j, I called that P2. So that's P2 right there, which means in my equation, what I'm trying to solve for is phi2. So in other words, K in my equation for rule 4 is going to be 2. Right? So the math for rule 4 goes like this. I want to find phi sub 2, which means first of all, everywhere I see k in the equation, I can replace it with 2 because I'm trying to find the kth departure angle. And the rule says that first and foremost for the departure angle, I'm looking for a summation through all of the zeros. Okay, it's the summation that has I equals 1 through m, and it's the kth pole, or in this case p2 minus zi. Okay, but you have to remember there are no zeros, so this entire summation is 0 for this example. From this summation, I need to subtract this additional summation from I equals 1 to n, which is going to sum through all of the poles. So P2, or pk, which in this case k is equal to 2, minus p sub I, plus or minus 180. So all of the terms are going to come from this summation, and inside of this summation there needs to be 3 components, right? Because I'm summing through all n of the poles. Okay, so we can clean this up a little bit. Phi2 is going to be, well, it's going to be 0 minus a bunch of angles. Okay, so a bunch of angles. The angle of P2 minus P1. So I is 1 first, so it'll be the angle of P2 minus P1 plus, right, it's a summation, so it's the angle of P2 minus P2 because I is incrementing up until you get to a value of n equals 3, plus the angle of P2 minus P3, and at this point I'm done. I've summed through all 3 of the poles. Then we're just going to remember that there's a plus 180 term that we have to tack on to the end. Okay, writing it symbolically like this is going to go a long way because it helps to keep your math a little bit more organized. Okay, so once you have it written symbolically like this, really all you have to do is to go back to your very organized sort of list of all of your poles and zeros and just plug in. Okay, so phi2 is equal to minus, right, let's just plug in. So the angle of P2, what is P2? Let me just consult my table, that's J, minus P1, which is equal to 1, plus the angle of P2, which is again J, minus P2 itself is J, plus the angle of P2, which is J, minus P3, which is negative J. All of that plus or minus 180. And if this is a little bit confusing, like for example, what is the angle of J minus 1? What helps me is to rewrite this into standard sort of complex notation. So instead of J minus 1, I'd prefer to write it as negative 1 plus J. What that does is allow you to visualize on the complex plane what that looks like. So negative 1 is here, plus J is here. So that complex value is right here in the sort of in this quadrant, and the angle of that complex number is that angle there, right? So I'm looking for the measurement from the positive real to this dotted line that passes through the point negative 1 plus J, which I can see by inspection is 135 degrees, right? So it might help you to sketch out what the complex number looks like, and it'll help you very quickly look at sort of what the angle should be. Okay, here's a nice one. The angle of j minus j, that's the angle of 0, which has no angle associated with it. So that's just 0. Plus, and then this guy over here, j minus negative j, I might rather write that as 0 plus 2j, right? And in this way, I can see visually 0 real component, 2 along the imaginary component, and that's the angle that I'm looking for. So clearly it's 90 degrees. So this is what the whole summation boils down to. Now there's a plus 180 term here. Again, it doesn't matter if you choose plus or minus. You'll get the same modulus of the angle regardless. And what we come out with ultimately is that phi 2 is equal to minus 45 degrees if I chose the negative 180, right? If you chose positive 180, you would get 315 degrees, but those are the same angle ultimately. Okay, one you just go negative, the other way you go all the way around positive, but you'll end up at the same point. So phi 2, we'll call it minus 45, which finally gives us a very clear picture of where these branches, of how they depart from their poles. Okay, so measured from a positive real, I should be going minus 45 degrees, and that is how the branch is going to depart from that pole. Right, so it's going to depart at minus 45 before ultimately converging on the asymptotes that were defined in Rule 3. Okay, and of course, according to Rule 0, we need to have symmetric plots, like so, which kind of brings up another point. Okay, probably what you found is that Rule 4, all this stuff that we just did, is pretty tedious. It's very annoying to apply Rule 4, so we want to apply it as little as possible. Okay, so in this case, where we had 3 poles, presumably we would have needed to apply Rule 4 3 times. But I would argue that 1 is sufficient. Right? You only need to apply Rule 4 1 time in this example to get a completely accurate root locus. And that's because any time you have poles or zeros on the real axis, there is no need to apply Rule 4. Okay? The reason is, well, by symmetry, poles and zeros on the real axis are either going to depart or arrive at 0 degrees or 180 degrees because they have to be along the real axis. And you can determine which one it is by simply applying Rule 2. Right? Rule 2 tells you which part of the real axis is going to be included on the real axis. On the root locus. Okay? Furthermore, anytime you have complex poles or imaginary poles, just pick one of them. Pick one of the angles to compute, and then use symmetry. Use Rule 0 to identify the conjugate departure angle, right? I mean, the root locus plots have to be symmetric, so as long as you find one of them, in this case phi 2 or phi 3, you would not have to solve for both. Okay? I don't want to overstate this. However, every term on the final exam, at least a handful of students will complain that they could not finish because they, ended up computing 6 or 7 departure and arrival angles when really they only needed to do 1 or 2, right? I mean, it's a very time-consuming process, especially on an exam situation where you have limited time, okay? So Rule 4 is outlined here, but specifically, according to Rule 4, you should minimize the number of times that you apply that rule. Okay? All right. The last and final rule. Okay, not nearly as bad as Rule 4. Rule 4 by far is the sort of most tedious. Rule 5 says the following. So I'll just write out Rule 5 first and then explain how it's used. Okay, so it says that break-in breakout points satisfy this equation, which looks awfully similar to the quotient rule from calculus, which is what Rule 5 is actually based on. Okay, so forgot to mention this part, for L of S defined to be some numerator coefficient of S divided by, some numerator polynomial in S divided by some denominator polynomial in S, then you just simply apply this quotient rule to solve for what are called the break-in, breakout points. Okay, so this is something I haven't really discussed yet, but let's look at an example to kind of illustrate this rule. I'll write it in two different ways because each way has its own sort of benefit. Okay, so this is some L of S that we computed by plugging into the characteristic function and then getting it into the proper form, 1 plus k times a bunch of other stuff. This is that bunch of other stuff that we got for one example. Okay, and so written this way, written the first way, it's very easy to compute the poles and zeros of L of S. We can see that first n is equal to 2, m equals 1, right? There's 2 poles and 1 0. Furthermore, the poles are at -1 and -2, and the 1 0 is at -3, right? So that's why writing it in this way is more convenient. What we see here is that on our S-plane, we have a pole at -1, a pole at -2, and there's a 0 at -3. Okay, so that's -3, -2, -1. How does this root locus, how is it going to look? First of all, we have all real poles and zeros. So what's interesting here is we need to sort of figure out, we still have to apply all the rules that we've learned so far, 0 through 4. Probably the easiest place to start is by applying rule 2, which again is to say what part of the real axis is going to be included on the root locus. So if we apply the vertical line test, we can see that everything between these two poles should be part of the root locus, because if I draw a vertical line between those two poles anywhere, at any point between those two poles, I am to the left of one pole, right? And 1 is an odd number. Okay, anywhere between this pole at -2 and the 0 at -3, I am to the left of 2 poles. 2 is not an odd number, so no part of the real axis between -2 and -3 should be shaded. And also everything to the left of the 0 at -3 is also going to be on the root locus, because everywhere to the left of -3, I am to the left of 3 poles and zeros. 3 is an odd number, which would indicate that portion of the real axis is on the root locus. Okay, so I do know that at least for now I can shade in all this stuff, and I know for sure that that's part of the root locus. What isn't immediately apparent by looking at rule 2 is the number of branches that are represented on those portions of the real axis. What I mean by that is this shaded region between these two poles, this actually has to represent 2 branches, because remember, branches always depart from the poles. So one of these, a portion of this line represents a branch that's leaving from the pole at -2 and heading off to the right, whereas another portion of this shaded region must represent a branch that's starting at the pole at -1 and heading off to the left. Okay, so this actually represents 2 poles. Likewise, this shaded area over here must represent 2 branches as well, because branches always terminate at zeros, right? So one of these branches has to end up at the 0 at -3, but also there are n minus m equals 1 branches that should approach infinity, and that would be represented by this portion that should go in that direction to the left. Branches cannot have multiple directions, right? So this over here must represent 2 branches, and this must also represent 2 branches. The only way to connect these 2 branches to these 2 branches is that they have to break away from the real axis at some point. Okay, So they can't cross over this real axis section. So at some point, the branches must break away from the real axis and head off into the complex plane. The same can be said for this section over here. These two branches must come from somewhere. And so at some point there must have been two branches that came in, met at a common point, and then split off into the left and right direction. Okay, so the only way that could happen without violating rule 2 is for the branches to actually do something like this. Right, so one will split off and head off around this way in a circular fashion. The other will head off and go this way in a circular fashion. And if I'm trying to be clear, I should emphasize that one branch goes one way, and it doesn't really matter if it's the branch that starts at this pole and then ultimately goes to the 0, or this branch may even go off to infinity. It doesn't matter. Okay, there's two branches. They always represent two poles of L of S. They're always going to exist as a function of increasing k. The point I'm trying to make here is that these points here are called break-in, break-out points. Right? So the branches either break out from the real axis or they break in to the real axis. And finally, rule 5 is a way to compute those break-in, break-out points. Okay? So for this root locus, I pretty much know everything about it. This is the shape that it has to have. One of the branches goes to infinity off to the left. All that's left to figure out is where are these break-in, break-out points. And to figure that out, we simply apply rule 5, which is fundamentally based on the quotient rule that you see here. Okay, so that's why this formulation of the transfer function is more convenient, because it's easier to take derivatives of the numerator and denominator. Okay, so let's compute rule 5 for this. It says that the numerator, s plus 3, times the derivative of the denominator. So 2s plus 3 is the derivative of this denominator, minus the denominator, s squared plus 3s plus 2, times the derivative of the numerator, which is just 1 in this case. That should be equal to 0. When you solve this equation for s, those are your potential break-in, break-out points. Okay, so what we get here is that s squared plus 6s plus 7 equals 0 after we clean up this first line. And what we end up with is that s equals minus 1.58 and minus 4.41. Okay, so rule 5 will not tell you which of these two roots is a break-in or break-out point. It's up to you to figure that out. Okay, but if you look at your root locus up till this point, it's pretty clear that minus 1.58 occurs between negative 1 and negative 2. So that's got to be the breakout point. And at negative 4.41, that's to the left of negative 3. So that's got to be the break-in point. Okay, so we've got a very clear, complete picture of what this root locus plot looks like. Let's see, one last thing that I'll leave you with is, in some scenarios, simply by applying the mathematics for rule 5, you will actually get a bunch of values for s. Okay, so you may get something that looks like this, or minus 1 plus or minus 2j. You might get a whole bunch of roots that satisfy rule 5 mathematically. Okay, but it's actually up to you to figure out which ones are valid and which ones are erroneous. Okay, so anytime you have a complex solution to rule 5, you can throw that out, because there's no way that a root locus branch could break in or break out of the real axis at a complex location. It just doesn't make sense, right? So you can throw out any complex or imaginary solutions that you get, but you also have to be wary of all of the real values that you compute as well, because minus 2.5 in this hypothetical scenario would fall between this pole and this 0 on this root locus, where we know there is no portion of the root locus plot according to rule 2. Okay, so a branch of the root locus plot will never break in or break out of the real axis at a point that is inconsistent with rule 2. In other words, I know there's no stuff happening between -2 and -3, therefore I should be able to throw out that solution to rule 5 and rule that out as a break-in or breakout point. Okay, any values that are left, you can assume that those are valid break-in or breakout points, which you can basically look at the configuration of your root locus plot and determine whether it's break-in or breakout. All right, so that's rules 0 through 5, the 6 rules for sketching the root locus plot. In the next lecture, we're going to look at exactly how do we apply root locus. We'll look at several examples of simply sketching the root locus, as well as actually using the root locus as a control design tool for designing control systems. Okay, so we'll do that in the next lecture.